A single project promised to change the course of the war in a matter of months. Germany invested enormous resources in developing secret weapons that, according to its leaders, could alter the outcome of the world conflict. They called them Wunderwaffen, the miraculous weapons of the Third Reich. The advances were real and deadly. The V-2 rockets could reach London in minutes, impossible to stop in flight. The jet aircraft exceeded the speed of any Allied fighter. State-of-the-art submarines operated with technology unknown until then. Each of these developments was conceived as the key to reversing defeats on the battlefield, but their production was limited, chaotic, and too late against the Allied advance. Could these weapons have really changed the course of the war if they had been deployed earlier? Were they visionary projects ahead of their time, or just impossible promises destined for failure? The total project, the Reich's technological gamble. In the year 1933, when Adolf Hitler assumed power in Germany, the National Socialist regime faced a complex geographical and strategic position. Surrounded by powers with access to colonies, abundant resources, and superior industrial capabilities, the country had to find mechanisms to compensate for its structural disadvantage. The solution proposed by the Nazi leaders was clear. Technological innovation had to become the tool capable of balancing the numerical and material disparity. From that moment, the search for advanced weapons ceased to be a complement and became a central axis of German military strategy. Hitler had directly observed the effects of technology during the Great War. The emergence of the tank, the use of aviation in combat functions, and the intensive use of heavy artillery had radically modified the way of waging battles. That experience convinced him that innovations could alter the military balance if they were introduced at the precise moment and on an adequate scale. After the defeat of 1918, attributed by him in part to the inability to sustain a pace of innovation against the Allies, Hitler assumed power with the conviction that the future of the new Reich had to be built on a solid and ambitious technological base. The logic that guided this gamble rested on three fundamental pillars. First, the scarcity of critical raw materials, such as oil, rubber, and certain metals, forced the resort to technical solutions that would compensate for the disadvantage in supply. Second, the concept of lightning war required weapons capable of disorienting the enemy through high-impact blows, which would paralyze the adversary's reaction before they could organize an effective defense. Third, the Führer's personal vision inclined decisions toward large-scale and monumental-looking projects, conceived not only as war instruments, but also as symbols of power. The result was that numerous armament programs were defined less by military efficiency criteria than by the political will to impress both adversaries and German society. This dynamic allowed technological development to transform into a propaganda showcase that absorbed considerable resources, even when mass production of conventional armament would have been more practical. In this terrain, the figure of Joseph Goebbels proved decisive. As Minister of Propaganda, he understood that technical advances could become psychological weapons. From 1943, when the defeat at Stalingrad marked a turning point in the war, he began to spread the idea of a secret arsenal capable of reversing the course of the conflict. Official speeches and the press controlled by his ministry described projects of extraordinary magnitude, presented as imminent, with the objective of maintaining morale on the home front and generating uncertainty in the Allies. The term Vergeltungswaffen, translated as retaliation weapons, became the most emblematic designation of this strategy. Applied to the rockets that began attacking London in the summer of 1944, the concept went beyond a technical description. It constituted a political narrative of revenge for the bombings suffered in German cities. Each official announcement transformed innovation into a promise of justice while hiding the delays and limitations of research programs. The projects were not mere propaganda fictions. There were real facilities, functional prototypes, and advanced research teams. However, military secrecy prevented the population from knowing the distance between announcements and practical results. Propaganda created the image of a futuristic arsenal about to be deployed en masse, although in practice production faced serious obstacles. Among the main actors of this technological race, Werner von Braun stood out, a young engineer specialized in rocket propulsion. After his first experiments in the 1930s, he was designated director of the Peenemünde Research Center, located on the Baltic Sea coast. There, the A-4 rocket was developed, later known as V-2, a liquid propulsion system with unprecedented capabilities in altitude and speed. Germany thus placed itself at the world forefront in missile technology, although the human and material cost of the program was enormous. Thousands of forced workers, in extreme conditions, participated in the construction of facilities and components. Another research front was headed by Werner Heisenberg, recognized theoretical physicist and Nobel Prize winner. Through the Uranverein, or Uranium Club, he explored together with his team the possibility of harnessing nuclear fission. The initial objective was to understand the viability of a controlled chain reaction that could open the path both to energy generation and to a weapon of unprecedented magnitude. Although the experiments never reached operational results, the mere existence of the program kept speculation alive about an eventual German development in the nuclear field. Albert Speer, Minister of Armament and War Production, informed Hitler about the progress and limitations of the programs. He privately acknowledged that German industry had achieved high levels of production in 1944, but warned that much of this effort was dispersed in experimental projects without immediate application. Political pressure obliged him, however, to present each innovation as a decisive advance. The German population perceived the materialization of these promises through the attacks with V-1 rockets against London in the summer of 1944. The sound of jet engines and the explosions reported by the press reinforced the idea that official announcements were true. However, daily reality showed another face. German cities were devastated by Allied bombings and the Eastern Front was progressively collapsing. This contradiction kept society in a state of constant expectation, waiting for a definitive weapon that never came to produce real strategic effects. The concept of Wunderwaffe or wonder weapon was expanded to encompass initiatives of various kinds. Projects of tanks of colossal dimensions, railway guns with unusual ranges, submarines with novel systems, fighters propelled by jet engines and intercontinental range rockets formed part of the repertoire in development. The breadth of the term kept alive the fiction of unlimited potential, although practical results remained partial. The limitations of the German research system were evident. The expulsion of Jewish scientists deprived the country of talents who later contributed to Allied programs such as Albert Einstein or Enrico Fermi. Added to this were rivalries between branches of the armed forces and direct political intervention in technical decisions, which dispersed resources and made it difficult to establish priorities. Each project competed to present itself as decisive, without a clear strategy of concentration of efforts. The secret laboratories scattered throughout the territory became symbols of this gamble. Peenemünde represented the best-known facility, but there were centers dedicated to research on new forms of propulsion, advanced materials, and control systems. To protect these projects, underground complexes were built that allowed production to continue even under constant bombing. The interaction between Hitler's personal vision, Goebbels' propaganda, and the work of scientists like von Braun or Heisenberg generated a singular phenomenon. The Wunderwaffen were not only weapons in development, but political and cultural constructions that gave technology a central role in the regime's survival. Investment in research, the creation of secret facilities, and the use of forced labor were justified as necessary sacrifices in the search for an arsenal that, according to official speeches, was to guarantee a victory that never came to materialize in the promised way. Steel Colossi, the Third Reich's armored ambition. The Wehrmacht began the war with an armored doctrine based on mobility, concentration of forces, and close coordination with aviation. The first Panzer models, relatively light, demonstrated their effectiveness in Poland and France during the first years of the conflict. However, the offensive against the Soviet Union in the summer of 1941 revealed a decisive surprise: the T-34 tank, a machine that far exceeded German armored vehicles in design, power, and resistance. The T-34 presented sloped armor that offered greater protection without excessively increasing weight. Its 76mm cannon could pierce German panzers at considerable distances. Moreover, the wide tracks gave it great mobility on muddy terrain, a crucial factor in eastern battlefields. Its simple construction allowed rapid repairs and large-scale production, ensuring that thousands of units reached the front in a short time. Faced with this challenge, the German High Command understood that it had to respond with heavier and better armed models. The Tiger Y was the first response. Introduced in 1942, it weighed more than 50 tons and was armed with an 88mm cannon derived from anti-aircraft pieces that had demonstrated effectiveness against armored vehicles. Its frontal armor made it almost invulnerable to most Allied weapons, and in individual combats it could face several enemy tanks with possibilities of success. However, the Tiger suffered important operational disadvantages: excessive fuel consumption, difficulty crossing bridges, and maintenance so complex that it required specialized technicians and long repair times. Tiger production also showed the Reich's industrial limitations. Barely a little more than 1,000 units were manufactured in 3 years, while the Soviet Union produced tens of thousands of T-34s in the same period. The disparity was such that individual technical superiority could never compensate for the numerical disadvantage. In 1943, the Panther appeared, designed to balance firepower, mobility, and production feasibility. It incorporated sloped armor like the T-34 and a high-velocity 75mm cannon. Its intermediate weight placed it between a medium and a heavy tank. However, the Panther's debut at the Battle of Kursk was marked by a high rate of mechanical failures. Problems in transmission and suspension left it out of combat in large numbers, even before facing the enemy. Over time, the failures were corrected and the Panther became a respected armored vehicle, but its complexity and cost continued to be obstacles for mass production. The next step in the scale of gigantism was the Tiger II, known as King Tiger. With a weight close to 70 tons and frontal armor of exceptional thickness, it was invulnerable to Allied frontal attacks. Its long 88mm cannon could destroy any enemy tank at great distance. However, production was scarce and mechanical reliability insufficient. Many units were rendered useless by technical problems before entering effective combat. The most extreme project was the Maus, a super-heavy tank designed by Ferdinand Porsche. With almost 200 tons of weight, it was armed with a 128mm main cannon, accompanied by another 75mm secondary one. Its frontal armor exceeded 200mm. Nevertheless, only 2 prototypes were built. Tests confirmed that the Maus was practically useless in real conditions. Its weight prevented the crossing of bridges and made its use in rapid operations unfeasible. Although a snorkel system was designed for fording rivers, the solution proved impractical in combat. Gigantism was not limited to tanks. German artillery developed the Gustav railway gun known as Dora with an 800mm caliber. This colossal piece required more than 1,000 men for its operation and could launch projectiles of several tons at distances exceeding 30 kilometers. It was used in the siege of Sebastopol in 1942, where it managed to destroy underground fortifications. However, its practical utility was minimal. Assembly required weeks, the tracks had to be specially reinforced, and once emplaced, it became an easy target for enemy aviation. The manufacture of such disproportionate weapons consumed enormous quantities of material resources and work hours. The same efforts would have been enough to produce dozens of conventional pieces with greater tactical impact. Moreover, Dora ammunition required exclusive manufacturing processes, complicating supply. The proliferation of models and variants in armored vehicles and transport vehicles aggravated logistical problems. Germany came to produce more than 100 different versions, which obliged maintaining gigantic inventories of spare parts and manuals in constant updating. Crews had to adapt to increasingly sophisticated systems, while the training of specialized mechanics could not keep pace. In practice, many units were left out of service for lack of adequate maintenance. The Battle of Kursk exemplified these limitations. While Tigers demonstrated destructive power in isolated confrontations, insufficient production and Panther mechanical failures reduced their strategic impact. Against this, the Soviet Union deployed tens of thousands of T-34s, manufactured with simplified designs and easily repairable in the field. The difference in approaches between Germany and its enemies was clear. While the Reich sought technical perfection of each individual machine, the Allies prioritized mass production of equipment good enough to sustain prolonged operations. This divergence defined the outcome on the land front. Punctual technical superiority could not substitute the industrial capacity and practically unlimited resources of the United States and the Soviet Union. The result was a German arsenal of machines impressive on paper, but too expensive, scarce and unreliable to alter the course of the war. The gamble on extreme innovation revealed its limits against the mass production of an enemy that could replace its losses quickly. Thus, the steel giants that had been born as symbols of power ended up converted into emblems of the Third Reich's strategic contradictions, leaving open the question of how this philosophy would transfer to other areas of war in the final years of the conflict. The disputed sky, machines that challenged the possible. The Reich's aviation began the war with a combination of refined tactical doctrine, experienced pilots, and aircraft well adapted to brief campaigns. The coordination between fighters and dive bombers had yielded results in the first European theaters, but that organizational design was conceived for operations of limited scope. When the conflict transformed into a war of attrition that connected the Atlantic with the Urals, the lack of strategic bombers with great operational radius and industrial insufficiency to sustain prolonged production rhythms exposed structural weaknesses. Under pressure from Allied air campaigns, political and military leadership bet on experimental programs that promised to alter the balance in the sky. The Me-262 jet fighter became the symbol of that ambition. Conceived before the outbreak of the conflict, it began its development with proven propeller cells while turbines matured. Its entry into service, already in an adverse scenario, brought to squadrons an unprecedented velocity vector for the era. The aircraft exceeded Allied fighters with ease, an advantage that in theory allowed selecting the moment of combat, firing and leaving the enemy envelope before formations could react. Its armament, concentrated in 4 30mm cannons, was designed to disarticulate defensive boxes of heavy bombers with few accurate bursts, a direct solution to the problem of growing density of Allied aircraft in German airspace. The technology that made it singular also imposed severe limits. The Jumo 004 engines, dependent on heat-resistant alloys, suffered very short service lives and obliged replacement and repair cycles that logistics could no longer sustain. The scarcity of nickel and chromium, aggravated by maritime blockade and bombings of metallurgical plants, reduced the availability of replacement turbines. The transition to jet flight also required specific training. Management of acceleration, gas input regime, and landing speeds required training that consumed months, a time that flight schools, subjected to evacuations, losses, and lack of fuel, could not guarantee. Hitler's direct intervention, who insisted on converting the Me-262 into a fighter bomber, added modifications and delays that postponed its use as a pure interceptor, function for which pilots like Galland had constantly advocated. The result was a production of more than 1,000 cells with a limited fraction available at the same time and an operational impact lower than expected for a system with clear performance advantages. The rocket dimension advanced in parallel. The V-1, first operational cruise missile, employed a simple pulse jet generally mounted on ramps on the Western European coast. It carried an important charge and flew at sustained speed with a rudimentary guidance system that combined gyrocompass and distance control, cutting fuel flow upon reaching the programmed trajectory. British defense soon adapted artillery, fast fighters, and captive balloons to intercept it. Even the destabilization maneuver by aerodynamic effect in flight was developed, pushing the missile's wing to alter its course and make it fall far from densely populated areas. Even so, the launch volume obliged redesigning defensive priorities and assigning specific patrols, raising the Allied cost of territorial protection. The V-2 took the technological leap one step higher. With liquid propulsion, inertial guidance, and a ballistic flight envelope that brushed space, its profile made it invulnerable to interception with contemporary technologies. It took off, ascended outside the range of fighters and artillery, and descended at hypersonic speeds over the target, where its charge detonated with devastating effects on structures and essential services. Precision, however, was limited and was often situated at the scale of complete neighborhoods, reducing military effectiveness against specific targets and forcing use closer to deterrence and punishment than to neutralization of concrete nodes. Production rested on underground facilities that employed forced labor in extreme conditions, a human and logistical cost that, compared with unitary operational effect, generated internal debates about its strategic convenience. Long-range artillery aspired to an intermediate solution with the V3, a multi-charge cannon arranged along the tube to increase exit velocity without resorting to a single massive detonation. The idea sought to batter urban centers from protected emplacements, but the installations were hit by specific bombings, and the program accumulated technical problems that prevented its maturation. At the same time, industry evaluated intercontinental range aircraft within the America bomber umbrella. Designs like the Me-264, the Ju-390, or the He-277 studied configurations to cross the ocean, launch charges, and return to Europe. The absence of reliable and powerful engines, chronic fuel scarcity, and useful load penalties derived from supplementary tanks emptied those concepts of operational viability beyond prototypes and studies. The most radical thinking was articulated in Eugen Senger and Irene Brett's Silbervogel, a suborbital bomber conceived to ascend with auxiliary rockets and traverse intercontinental distances through successive bounces in dense atmospheric layers. Calculations incorporated surface control at hypersonic speeds and thermal protection for partial re-entry, a theoretical anticipation of problems that aeronautics would solve decades later. The project did not pass models and technical notes, but illustrates the horizon that German leadership wished to reach while the front compressed inland. In point defense, the Me-163 Comet rocket interceptor bet on almost vertical climbs and speeds close to 1,000 kilometers per hour. Its propelled autonomy lasted few minutes, which required taking off at the exact moment to coincide with enemy formations, execute one or two passes, and glide home, landing without conventional gear. The fuel, extremely corrosive, caused ground losses and required complex safety protocols. The system shot down a reduced number of bombers and made clear the difficulty of translating extreme performance into sustained effectiveness when the combat window is minimal and logistical requirements exceed the reasonable for continuous defense. Experimentation with flying wings, represented by the Ho-229, introduced a geometry that reduced frontal signature and distributed lift without classic fuselage. With Jumo turbines and mixed structure, it offered a favorable drag ratio and a contour potentially less visible to primitive radars of the era. An accident in tests and war calendar pressure closed the possibility of evaluating it in service, but the type anticipated evolution lines that would later be retaken in other countries. The fundamental problem was dispersion. Instead of concentrating resources on a few systems with high probability of sustained production, industry sustained dozens of programs in parallel. Competition between manufacturers, rivalry between branches, and the Führer's personal intervention in technical decisions diluted priorities. The result was a mosaic of excellent prototypes on paper, short series without critical mass and assembly lines interrupted by bombings and lack of materials. With rationed fuel, pilots with decreasing flight hours and training centers relocated, even the most promising aircraft lost operational impact. Air defense needed abundant interceptors, integrated radars, fighter control, and spare parts in constant flow. Instead, it received high-performance pieces with fragile logistical chains and overly narrow availability windows. As the war advanced, punctual superiority of speed or firepower was not enough to alter the daily pulse of Allied incursions. Industrial cities continued under attack, refineries and alloy plants suffered recurrent interruptions, and each passing month eroded the material base that allowed flying, maintaining, and replacing. In the air, as on land, the gamble on extraordinary innovation clashed with an adversary capable of producing, training, and sustaining during prolonged periods. Thus, air dominance was marked by a sharp contrast between technological ambition and the reality of total war, a contrast that opens the way to observe how the Allied response adapted and how those lessons shaped, beyond the conflict, the subsequent development of aviation and missiles. Shadows in the Atlantic, German submarine warfare. From the beginning of the conflict, the German Navy faced an essential contradiction. Hitler never granted strategic priority to the construction of a great fleet, but submarines became one of the most effective instruments to pressure the United Kingdom. Admiral Karl Dönitz sustained since before the war that only an unrestricted submarine campaign could force the British to negotiate, cutting merchant traffic that kept their economy active. His calculations estimated that a sustained force of 300 submarines would suffice to strangle transatlantic routes. During the first years, that vision seemed confirmed. The U-boat fleet of Type 7, backbone of the German submarine armada, possessed sufficient autonomy to operate in the North Atlantic and was armed with torpedoes and deck guns adequate to destroy unprotected merchant ships. The so-called happy time between 1940 and 1941 allowed submarines to act with relative impunity near the British Isles and later on the American coast. The Wolfpack tactic, with several submarines converging on the same convoy, multiplied sinkings and exposed Allied vulnerability. Operations benefited from technological limitations in defenses. Night surface attacks reduced detection probability and radio communications coordinated unit concentrations. Torpedoes were fired at short distance, increasing precision. However, the panorama changed rapidly. Centimetric radar began detecting periscopes and conning towers at great distance, even in darkness. Perfected sonar improved underwater location, and new weapons like the Hedgehog increased direct impact probability. The introduction of escort carriers and patrol aircraft closed the Atlantic air gap, forcing submarines to remain submerged for longer periods and limiting their mobility. Germans reacted with innovations. The acoustic torpedo Zaunkönig followed propeller noise, increasing hit probabilities, although it was soon countered with Allied towed acoustic distraction devices. The snorkel allowed recharging batteries underwater, reducing exposure but did not completely eliminate radar detection. Over time, the Battle of the Atlantic transformed into an industrial production competition. While U-boats sank ships, North American shipyards delivered Liberty-type freighters at a rhythm that exceeded losses, ensuring constant growth of Allied tonnage. In that context, Germany developed Type 21, considered the first submarine truly designed to operate in prolonged submersion. It incorporated high-capacity batteries, silent electric motors, and an optimized hydrodynamic hull. Its underwater speed exceeded that of many escort ships, which would have allowed maintaining contact and escaping more effectively. Torpedo reloading was rapid and could launch complete salvos in few minutes. However, the program began too late. Little more than 100 units were completed, and only a couple performed patrols without managing to sink enemies. Quality problems derived from hurried modular construction further reduced their reliability. Type 23 transferred these principles to a coastal format. Smaller, faster, and with lower displacement, it was designed for the North Sea and Baltic. Its size made detection difficult, and its characteristics allowed it to operate with some success in the last months of the war, sinking some merchants in British waters. These models, although promising, arrived when Allied supremacy in air and surface was already complete. Besides submarines, the German Navy deployed fast attack boats. The S-boats, which the Allies called E-boats, operated in the English Channel and North Sea. With speeds exceeding 40 knots and torpedo and anti-aircraft armament, they performed nocturnal incursions against convoys and ports. Their tactical effectiveness was recognized, as evidenced in the attack on the Allied exercise at Slapton Sands before the Normandy landing. However, the limited number of units and growing air coverage reduced their strategic influence. In contrast, large surface projects reflected the lack of coherence in naval planning. Plan Z had foreseen gigantic battleships, some of more than 100,000 tons with main pieces of more than 500 millimeters, capable in theory of challenging the Royal Navy. Construction never passed the design table, and the loss of Bismarck in 1941 convinced Hitler that battleships were expensive and vulnerable. The sinking of this ship and subsequent neutralization of Tirpitz led to replacing Admiral Raeder with Dönitz in 1943. Dönitz maintained his faith in submarine warfare. He insisted that massive deployment of new models could change the course of the war, hindering Allied logistical routes before a continental invasion. Construction moved to underground facilities like Mittelbau, where thousands of prisoners worked in extreme conditions in an effort similar to rocket programs. Submarines were assembled in modular sections to disperse production and reduce vulnerability to bombings. Even so, lack of fuel, loss of veteran commanders, and Allied air pressure severely limited the effectiveness of new systems. At sea, as on land and in the air, the German gamble on advanced innovations clashed against Allied industrial and material superiority. U-boats continued representing a constant threat, but their capacity to alter the course of the conflict progressively reduced. The transition toward truly submersible submarines opened a new stage in naval technology, although it arrived too late to influence the immediate outcome of the war. That technical legacy posed questions about subsequent development of submarine forces and about how other powers would assimilate lessons from the Battle of the Atlantic. Science at the limit between the real and the fantastic. German scientific effort unfolded within a contradiction that accompanied it from the beginning. The country had first-level physicists, engineers, and mathematicians, but regime ideology, internal struggles for resources, and systematic exclusion of Jewish scientists reduced the possibility of transforming that potential into strategic achievements. The most ambitious projects of the so-called wonder weapons were situated in intermediate terrain between applied science and technical speculation. The Uranium Club, formed in 1939, brought together figures like Werner Heisenberg, Carl Friedrich von Weizsäcker, and Kurt Diebner. These scientists understood the implications of Otto Hahn and Fritz Strassmann's discovery in December 1938. The bombardment of uranium nuclei with neutrons released enormous quantities of energy. The possibility of a chain reaction opened both electricity generation and war applications. Military commands showed immediate interest, although progress was slow. Heisenberg considered a nuclear reactor viable, but doubted that it would be possible to obtain a usable weapon in the timeframes that war imposed. The group worked with metallic uranium suspended in heavy water, seeking conditions to sustain a controlled reaction. The most advanced laboratory was installed in Haigerloch, in the basement of a church, where an experimental reactor was mounted with several hundred uranium cubes in a cylindrical heavy water tank. Tests failed to achieve criticality, and in April 1,945 Allied forces captured the ensemble within Operation Alsos. Allied reports confirmed that Germany was far from producing a nuclear weapon. The lack of dedicated resources, dispersion in small research groups, and priority given to other projects limited progress. The expulsion of Jewish scientists deprived the program of talents who later proved decisive in the Manhattan Project. The interrogation of main German physicists at Farm Hall near Cambridge revealed that they were unaware of the magnitude of American achievement. Recordings showed surprise at the actual use of nuclear weapons in Japan and calculation errors around necessary critical mass, unmistakable sign that they had not reached practical mastery of the question. Alongside the nuclear program existed projects that bordered on speculation. The so-called ray weapons awakened interest in some sectors. Various teams explored the possibility of concentrating electromagnetic energy in destructive beams. Some studies used high-frequency radiation, others tried to create particle rays. An officer named Schröder Strantz presented proposals to build a weapon based on X-rays that, according to him, would pierce armor or disable aircraft engines. Documents suggest that the SS financed partial tests, but none advanced beyond rudimentary prototypes without military application. There were also attempts to design unconventional aircraft. Rudolf Schriever elaborated schemes of circular apparatus with turbines on the perimeter capable of taking off vertically and flying at great speed. Victor Schauberger, Austrian inventor, worked on propulsion concepts based on what he called implosion, a centripetal suction system inspired by natural fluid dynamics. He claimed the phenomenon could generate thrust without conventional combustion, although none of his models worked in practice. Available archives show that these ideas remained in preliminary stages with studies and reduced-scale models. The subsequent legend of Nazi flying saucers fed on these secret projects, but no evidence exists of operational aircraft in combat. In contrast, Eugen Senger and Irene Brett's Silbervogel project represented a more solid ambition. This suborbital bomber was to ascend with auxiliary rockets to high atmospheric layers and then traverse intercontinental distances through successive bounces in denser layers. Calculations indicated it could take off from Germany, reach New York, and continue to the Pacific. Senger elaborated detailed studies on aerodynamic control at hypersonic speeds, thermal protection against friction, and propulsion requirements. These problems anticipated questions that decades later faced shuttle engineers and re-entry vehicles. The project never passed plans and calculations. Materials to withstand those extreme conditions did not exist in the 1940s, nor did industrial capacity for a program of such magnitude. Political decisions directly influenced research. The expulsion of Jewish scientists from 1933 removed figures who later were essential in the United States, such as Albert Einstein, Enrico Fermi, or Leo Szilard. The intervention of leaders like Himmler or Goebbels in resource distribution favored flashy or propagandistic projects instead of more discreet but viable research. This politicization generated an environment where science was subordinated to propaganda and ideology. Extreme secrecy aggravated limitations. Teams worked isolated, without information exchange, which prevented collective advances. Compartmentalization avoided related disciplines from collaborating and reaching synergistic results. Allied perception of German science was an additional factor. Fear that Germany would produce revolutionary weapons motivated bombings like that of Peenemünde in August 1943 and systematic capture operations of scientists through programs like Paperclip in the United States or their Soviet equivalents. That attention was due partly to real achievements in rocketry, but also to Nazi propaganda that inflated expectations about capabilities in development. The nuclear program, in particular, had fallen behind because German scientists themselves considered it would require years of work before obtaining practical results. When Albert Speer consulted the viability of an atomic weapon, experts recommended dedicating resources to projects with immediate application, such as rockets and jet aviation. The contrast between real achievements and propagandistic perceptions explains the persistence of myths about Reich secret weapons. In this frontier between science and speculation, the Third Reich produced advances that influenced subsequent technologies such as ballistic missiles, but also dedicated resources to ideas that never passed theories. Nuclear fission was understood in its principles, but without material means to transform it into a weapon. The Silbervogel showed advanced vision, but remained outside the reach of metallurgy and propulsion of its time. This mixture of genuine innovation and fantastic projects marked German research, reflecting tensions between scientific ambition and practical limits in a regime where politics dictated the course of technique. Thus, the Reich's scientific panorama presented itself as an incomplete mosaic of achievements and promises, opening questions about how these experiences would shape technological developments of the post-war period. Wonder weapons or impossible fantasies? The evaluation of the so-called German wonder weapons requires distinguishing between technical achievements and real repercussion in the conflict's development. The program constituted one of the most ambitious military research efforts in history, with innovations that anticipated subsequent technologies. However, strategic impact was reduced compared to invested resources and to expectations created by regime propaganda. One of the main obstacles was systematic dispersion of resources. Instead of concentrating on a few viable projects, industry multiplied initiatives in parallel, driven both by rivalries between branches of armed forces and by manufacturer competition for state contracts. The result was a fragmentation that diluted the potential of the most promising advances. The Me-262 jet fighter illustrates this situation. It was a revolutionary aircraft, superior in speed to any contemporary Allied model, but entered service when Germany had already lost control of airspace. Its production, of little more than 1,000 units in 2 years, resulted marginal against volumes of conventional fighters manufactured by the United States and Soviet Union. The scarcity of pilots trained in new technology further limited its use. The Type 21 submarine represented another decisive advance in concept, designed to operate submerged during long periods and anticipate post-war submarine warfare. However, barely a couple of units performed patrols before the end of the conflict without sinking enemies. Although little more than 100 were completed, that figure was insignificant against Battle of the Atlantic needs. Quality problems in hurried construction further reduced their reliability. German inability to sustain mass production was the factor that nullified any punctual technical advantage. The Soviet T-34 tank, American Sherman or British Spitfire did not represent perfection, but were effective enough and could be produced in quantities that exceeded losses. In contrast, Tigers and Panthers, more powerful individually, were manufactured in thousands of units against tens of thousands of their adversaries. This difference revealed opposite philosophies. Germany prioritized technical excellence of each machine, while Allies sought robust and easy-to-manufacture and maintain models. Hypothetical scenarios about anticipated deployment of German weapons show structural limitations. Even if the Me-262 had been available en masse in 1942, problems of maintenance, fuel, and pilot training would have reduced its impact. Similarly, if Type 21 and 23 submarines had been operational in 1943, Allied industrial superiority in naval construction would have countered their effects. The decisive factor was adversaries' material capacity. The United States could produce more than all other belligerents combined, while the Soviet Union absorbed colossal losses without collapsing. Germany, in contrast, depended on limited resources and was geographically surrounded, making it impossible to sustain a prolonged war of attrition. The impact of secret weapons manifested more in psychological terrain. Joseph Goebbels' propaganda presented them as symbols of resistance and revenge. V-1 and V-2 rocket attacks on London did not break British morale nor modify policies, but showed that Germany still conserved technical capacity. For German population, promises of decisive weapons prolonged hope and reinforced will to resist even when defeat was evident since late 1943. Comparison with Allied models highlights basic principles of industrial war. The T-34, of simple construction, could be manufactured in dispersed factories and repaired in campaign. The Sherman, although inferior in individual duels, compensated with volume, artillery and air support, and tactical coordination. The Spitfire evolved incrementally, maintaining continuity in training and logistics, which allowed sustaining effective air forces throughout the war. In contrast, each new German design required different training, different manuals, and complex maintenance chains. Political intervention further distorted research. Hitler favored spectacular projects, such as Maus tank or Dora gun, which consumed strategic materials and work hours without generating equivalent operational benefits. Leaders competed to attract the Führer's attention with flashy ideas, while more practical initiatives were relegated. This politicization created incentives that privileged radical innovation over gradual improvement of existing systems. The legacy of secret weapons extended beyond German defeat. Allies captured documentation, prototypes, and scientists who fed their own programs. Operation Paperclip transferred specialists like Werner von Braun to the United States, who later were essential in the development of intercontinental ballistic missiles and in the space program that culminated in the moon landing of 1969. The Soviet Union made equivalent captures, incorporating German technologies into its arsenal. Type 21 design directly influenced post-war diesel-electric submarines. The Horten brothers' flying wings anticipated features of later stealth aircraft. V-2 technical principles laid foundations for space rockets. These developments show that although wonder weapons did not alter the immediate result, they did shape military technology of the second half of the 20th century. The paradox is that the greatest impact of these weapons occurred after the war they failed to decide. Germany was defeated before its projects reached operational maturity, but victorious powers took advantage of those advances. In this way, the search for extraordinary solutions left a legacy that transcended the Third Reich, opening a new scenario in post-war technological confrontation and raising questions about the role of science in future conflicts.